Good morning, everybody.
Good morning.
So thank you all so much for coming and choosing this session. My name is Ronnie Thomas, and I'm from Atlanta, Georgia, and I'm here today to share with you my passion. This is what jerks me out of the bed each morning, fun, weird science. And today we're going to talk about it and show how it can be used to increase excitement in our classrooms and be used as a way to ensure that we're being inclusive in our approach to STEM education. So that little guy on the screen there used to have a head full of hair. And that young lady is about ninth grade, eighth and ninth grade. But today we're married and we have three pretty amazing children, Ramaya, Layla, and little Ronnie. So a little bit about me. I'm from Birmingham, Alabama originally, but I've been living in Atlanta the last 20 years where I've taught school in a variety of settings from public, charter, to private. And I've had some pretty amazing experiences. My last assignment was a STEAM coach at Atlanta International School.
Good morning.
Prior to coming there, I was fortunate to be chosen by my peers to serve as teacher of the year twice. And one of the highlights of my career was doing a NASA research project where we worked in reduced gravity environments to see if bubbles would last longer.
I need to talk directly into it.
But none of that almost happened because about 5 years into teaching, I almost left to become a truck driver.
Thank you.
I got burnt out. At that time in Atlanta, a truck driver made more money than a new teacher.
The sound
And it's probably still the same.
welcome to our presentation
But
on coaching
science
equity.
saved my life.
I'm Andrea Galler.
I started going to attend different professional development opportunities,
San Jose State.
and I would bring those skills and activities back to the classroom. My children would go crazy, and it became a high trying to recreate that level of excitement in the classroom.
About what's going on at Prospect High School. We're hearing so many.
And you're going to have this slide deck available to you as well, where you can possibly look at attending some of these professional development opportunities
Great
yourself.
to see what they're doing. So I need to stand in this box. I apologize if
So,
I'm fidgeting because I'm used to
After I got all this great
we're going to start
approaches, I'm not sure what, I guess that's the,
what is
yeah, but we'll keep
inclusive
moving.
education?
So I started taking the things that were working in my classroom really well and showing other teachers how to engage their children in science as well. And in Georgia, as here in California, we have the term phenomena, right? Where we ask kids to look at things that happen in nature or things that are engaged by humans or by us, but they're looking at the science behind that. So today our goal is to use a variety of different demos that can be used to hook the kids' attention to go a little deeper into those concepts. When I first began teaching, we were so focused on math and ELA that we only gave about 20 minutes to teaching science. And much of that 20 minutes was reading about science. Oh, I hate when we just read about science. Because in order for it to be engaging and impactful, students must do science. I also became concerned about how children viewed themselves and who they thought of when they thought about a scientist. So as we're being inclusive in our approaches, it's important that we show and engage our students in a variety of STEM and sciences individuals that look like them. So here are my 3 reasons why students must do science.
So sometimes that's girls.
Oh, okay. Awesome. Let's give her a big hand for saving the day. Reason number 1, it allows children to involve in authentic curiosity. I have a 5-year-old son. He has a million questions. And I love it. But he's authentically curious about the world around him. And I don't want to stunt that by not answering as silly as the question may be. I don't want to stunt his growth by not answering or engaging him in that question. Most of our classrooms, kids just like owls. They regurgitate what they've been taught and they spit it back out to us for a test. It allows kids to have real life connections, and it allows them to see themselves as scientists and engineers and overall problem solvers. So, you guys ready? You might want to clear your tables because this is an all-in. This is an undivided attention workshop. So before we begin, we're going to stretch our brains. So hold your thumb up like this and point to your thumb like this. And when I count to 3, I want you to repeat the motions of my fingers. And we're going to stretch our left and right brains. 1, 2, 3. You're forcing the left and the right side of your brain to work together. And the more you do it, the better you're going to become. I couldn't do it in the beginning also. But you start off going real slowly, and over time, you'll be able to do it quickly as possible. Now, our first engagement, we're going to save Fred. Fred, he never did get those swim lessons as a kid, but Fred loves boats. And he went out to Lake Merritt in Oakland, and he wanted to ride his boat. But something happened. Fred's boat ended up capsizing, and we need to help save Fred. This is going to be a really great opportunity for you to work on your communication and collaboration skills. So with a partner, take a cup, 2 gym clips each, 1 gummy worm and 1 gummy lifesaver, and set it up like you see it on the screen. Now, the gummy lifesaver represents Fred's life jacket. We need to work together to come up with a plan where we can put Fred's life jacket on his body. But here's the thing. We cannot touch Fred, the boat, or the life jacket with our hands. We can only use those 2 paper clips. So take your paper clips, open them up, fold them, stretch them in any desired position. You cannot skewer Fred. We cannot make a Fred's kebab today. But you're going to have to talk first, strategize, game plan, and talk about what would be the best approach to get that life jacket from underneath the boat. Fred cannot fall off the boat. But we have to put him through that circle. Put Fred through that circle in the life jacket. I'm going to give you about 30 seconds to brainstorm and discuss with your partner. Well, then that's going to be the boat. Then once you get the boat turned back over, then Fred's going to have a hole in his boat. Please save Fred. Say again? Yeah, he has to be inside there.
He has to be inside this?
Yes. So you have, so you should have 4 paper clips.
4?
Yeah. Is the life jacket on him?
Is that enough? Or does it need to be on more?
On him, I would try to go center.
He's surviving.
He's surviving. We wanted to make it home alive and thrive. Now, one of the great things about engaging kids in science and STEM, it allows them to work on and develop those soft skills. Now, we know every student won't be the next Elon Musk, But those soft skills, communication, listen to the talks you're having right now. They can work on their communication skills, their team working skills. Awesome. Fred is saved over here at this table. Give him a big hand. So, share, if you don't mind, please share your strategy. Please share your strategy.
I couldn't puncture Fred. I couldn't make Fred come off, so I used this and threaded Fred through the line.
Oh,
Like a needle.
awesome. Awesome.
Fred wasn't stabbed, no. I just pulled him through.
Good stuff. Give him a big hand. Now, you're welcome to keep this and take it with you and try it tonight at your local pub. Now, for the sake of time, I know it's wonderful and engaging, and please take it with you, but there's more. There's more. To help develop those soft skills, it's very important that we're able to give students a chance to work together. I think many of the problems in our society come from the lack of talking to each other. You know, if our countries just talk to each other, there's enough resources on the earth to sustain everybody, right? But if we continue to allow greed to drive our motives, it's not going to be good for anybody. So many of our problems can be solved by talking and working together, and many of our perceptions can be changed when we have a better understanding of people who may be different from us. Would you agree? So, to demonstrate that, we're going to do the pyramid cup bill. So at each table with a stack of cups, we need about 5 people. So come around to a table, and no, about 4. Give us 4. 4 people at each cup stack. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Make sure you have 10 cups in your stack. And I like to call this next instruction, unstack your cups and turn them in spring break position. You guys understand? Good job. Yeah, this is my kind of group. Now, does everyone have 10 cups in their stack? Now, working with your team members, you're going to build a pyramid. You're going to take the cups, you're going to turn them upside down, put 4 cups on your bottom, 3 cups on your second tier, 2 on your third tier, and 1 cup remaining on top. Go ahead and build that pyramid now, please. That's a different design. All right, we have 1, 2, 3, 4. That was a good, I like that approach though. That was a different, I've never seen that approach. I think I like that though. I love out of the box thinking. That was a good attempt. But you all get the point, right? Yeah. Give yourselves a big hand. Now, unstack those cups and turn them back into spring break position. You are going to rebuild this pyramid. Except this time, you cannot touch it with your hands. Each person will grab a string, and you will pull on your string. Go ahead. You will pull on your string to expand and contract your rubber band. And you only can build a pyramid using this string and rubber band contraption. If a cup falls and you touch it, you must turn it back in spring break position. All right? So the only thing that can touch the cups are the strings and the rubber bands. Awesome. Now, once you receive your rubber band and string contraption, you may begin. So they should be in spring break position. No. Only can touch with the string or the rubber band. Notice your communication skills. It may help to stand. Awesome progress, good progress. Oh! You can, but you have to put it back in spring break position. Oh! Yay! All right. Let's give them a big hand. Now, once again, someone at the table, you're more than welcome to have this setup as well. It will go off really well tonight with the family at home during dinner time. All right. Moving forward. Please feel free to stop me if you have any questions that may arise. I may talk fast, but only because I want to make sure that we fill all of our time together. Take out your phones, take a big picture of Fun Weird Science. If you're on social media, we're on Facebook, Instagram, and Twitter. And we also have a YouTube channel on Fun Weird Science TV. Now, what is in my hand? Paper towel. 5, 4, 3, 2, 1. What am I doing to the paper towel? I'm folding it. What's changing? The size and the shape. But it's still what? It's still a paper towel. Can I reverse the changes that were made to the paper towel? Yes. So that would be indicative of a physical change. Would you agree? Now, what if I was curious enough to light this paper towel? What would happen? It would burn. How will we know it's burning? We'll see fire. We'll feel heat. We'll smell what? Smoke. And we might even see this new substance called ash. Could I reverse that change? No. I'm not going to do it, though. But I am going to light this paper. So we have something called flash paper that has been chemically altered. It's been saturated and dried in a chemical called nitrocellulose, And the cool thing about it, when it burns, it leaves no smoke or ash. So imagine walking to your classroom, doing this, and walking away. And then you had your kids write about, where did that paper go? And like that's their creative writing piece for that day, right? But it's really an amazing conversation starter. Like why does this paper burn with no ash or smoke? I mean, I could do this all day. This is so fascinating to me. One more time.
Hold on.
Oh, man. That was a good one. Give him a big hand. So would you agree that would grab your kids' attention?
Yes.
And then there are so many ways you can build off of that to have additional conversations. But once again, flash paper, also known as nitrocellulose, it's been put in nitric acid, so it burns instantly with no smoke, no ash when touched by flame. So that made me think, if this paper burns and this paper disappears, what would happen if we burned money? Does anyone have a bill larger than a 1? I promise you, it's the bigger the bill, the bigger the thrill for this next one. Like 20s and 50s go really well. Anyone care to donate to my lunch fund for the day? I'm starving, but seriously. Anyone with a larger bill? I see somebody reaching. I'm telling you, the bigger the bill, the bigger the thrill. Come on, give him a big hand. So you're gonna come up and do it yourself, because if you burn your money, you have nobody to be mad at except yourself. So, all right, so safety goggles first, and we're gonna measure out 90 milliliters of 70% alcohol. It's 70% alcohol. So I'm going to measure out 90 milliliters of 70% alcohol. Now, when I was a kid, my parents told me to not burn my money. I apologize about that. What do you think they meant by that? To not spend it? Why? Don't spend it unwisely. All right. Now, this is a great chance to infuse vocabulary. You can have the kids identify the shape of this science tool and tell you the name. Who can give us the name of this tool? And at the end of last year, it did what? It's going to 6th grade next year, so it graduated. So it's a graduated cylinder. All right, so we're going to pour. Yeah, somebody got it. Thank y'all. Somebody got my joke. I was like, man, you left me out there for a while. So you're going to pour the alcohol into the cup. And then we're going to measure out 30 milliliters of water. And now we're getting ready to make a solution. And I'm talking to you like this, not to insult anyone's intelligence, but I'm just trying to model how I would engage the children in the conversation about the vocabulary. So when your lunch you packed this morning had a sandwich perhaps, right? And we had bread, meat, cheese, tomato, lettuce. When you add those things together, nothing changes the individual property, right? The bread's still the bread. It may be soggy, but it's still bread. The meat's still the meat, cheese still the cheese, and so on. Would you agree? If you change your mind and decide you don't want lettuce anymore, you can remove it, right? So we have a mixture. So now pour that water into the cup of alcohol, and here we have a solution. So we cannot separate it, right? So now you're going to take your $5 bill and these tongues, and you're going to saturate, put your bill in there, make sure it gets saturated. I heard the more saturated the bill, the better its chance of return. All right, so you're going to take it out. If we can bring the lights down just for one moment. And you're going to open it up and hold it by the edge. Hold it up and out with using the tongs. Yeah, there we go. Perfect. I'm going to move that just in case. And we're going to light it. What do you all think is going to happen? The bill will disappear? Oh, he'll be really mad then. But it's possible. It is really possible this bill could disappear. What other hypothesis do you have? It will be protected in some way.
It's going to burn the alcohol, but the water's going to
Burn the alcohol, but the water put it out. Let's dip it in one more time, because I don't know. Right? All this waiting, I don't know. I don't want to delay. All right. Take it out. All right. Let's see. Here we go. Up and high. Oh, man. Give him a big hand. And it's almost dry. So what do you think happened?
I'm not sure, but I think it just kind of lived around the bill and just burned out the outside, and then it's done.
I love it. So if we would have used only water, what would have happened? Nothing, right? Because water is non-flammable. If we would have used all alcohol, it would have burned because it would have charred, right? But what we saw, the water, say absorbed. Once again, just modeling how I would engage the children in the conversation. But the water absorbed the heat energy, and what you saw burning was the alcohol on the top of the water. And before the bill could reach its point of combustion, the alcohol evaporated and burnt out. Give them a big hand. So,
Can I grab a paper towel?
yes. What do you think would happen if we put a paper towel in that solution and burned it? Huh? More porous. You know we got to test it, right? Let's see. Things do not always work the way that we think they should in science, but there's no failure. We just find ways to do it differently. So the paper towel is more porous, so someone hypothesizes that it may burn and char. Safety first. Yeah. So it burns longer, but it does not what? Doesn't char. Pretty interesting. Pretty interesting. So talk to your neighbor about how you can use one or all of those demonstrations in your classroom for a moment. No. Now, what's in my hand? A water jug. What's inside the jug? Air. There's air inside of it. If you look at the bottom of the jug, what shape? I almost said it. What shape do you see? There's a star, but the outside shape is what? A circle. And we say the distance around a circle is called the what? Circumference. Which circumference is bigger? The top or the bottom? The top. So, what do you think would happen if everybody in this room tried to go through that door at one time? We'll get stuck, right? The heat started to build, people start sweating. Some people might even start saying some words that are not approved by the district. But it would be very challenging, right, to get out the door. So what do you think would happen? What do you hypothesize would happen if we put alcohol in this bottle and drop a lit match inside of it? Talk to your neighbor for a moment. And share your hypothesis with your neighbor. Because we're going to do it. Now, what do you think we're going to see during this investigation? What are we going to see? I'm going to put alcohol and drop a match inside. We're going to see a flame. What color would that flame be?
Blue.
Blue. Any other colors could possibly be? Green. Orange, green, red, yellow? I don't know. What do you think we're going to hear? Woof. Make the sound you think we're going to hear. Whoosh. Now, if you hear this sound, listen very carefully. If you hear this sound, it has nothing to do with this experiment. There's somebody trying to slip one in from their breakfast. So we're going to see a possible variety of colors of flames. We're going to hear some sounds that some say a whoosh sound, right? Touch the bottle. How does it feel?
Solid.
Feels solid, temperature-wise.
Oh, room temperature.
Room temperature. All right. We're going to measure out. I know it says about 60 on the board behind me, right? I have never really been that well following directions. But the more you do this experiment, there's a residue that builds up. And that residue sometimes reduces the reaction. So we're going to go about 90. Air inside the jug, correct? Now what do we have in there? In what state? And I'm using 91% alcohol. I can smell the alcohol. So that means that there's a second state of alcohol. And what would we call that? The gas. So we have air, liquid alcohol, and alcohol vapor. Saturate the bottom and the sides. If you have an iPhone, this might be a great time to record in slow motion. If someone can bring down the lights, and you can still see in the camera, correct? The jug here. For our listening and viewing audience during the stream. So we're going to drop a lit match inside, and we're going to look and listen for the reaction. 3, 2, there's your whoosh. Did everybody get a good shot? Lights back up. You would have to pour it out and then dry it a little bit. But what do you see at the bottom? Liquid. Is that alcohol? What is it? Yeah, condensation, right? When we dropped that match in, the alcohol vapor and the oxygen created a combustion. And air was being forced out of the bottle. At the same time, air was being sucked inside the bottle. And that alcohol evaporated. It went up top, cooled off, and now it condensed. And if you look closely, you can see a cloud starting to form. So now we can talk about the water cycle, along with these internal combustions. Talk to your neighbor and share your thoughts about that demonstration. The Whooshing Bottle. You can purchase this bottle at Walmart. I would definitely recommend using a long match. When I first started doing it, I had gloves and like tongs, and I would drop the match in. When I first really started doing it, though, I had like those long grill, and just all you heard was, my hand was so nervous. So definitely the long matches would be the best way to go. But now that cloud is more defined inside that bottle. Really? Now, one thing that I would like to do at some point is to build a contraption where I can turn this bottle upside down, because I know from watching and observing, it's forcing its way down, right? I want to see what that looks like. So maybe if I can build a contraption to make it go up, or have it attached to a PVC stand to see how many loops it could make. So I don't know. Think about it, try it out. Practice at home first to make sure you're comfortable with doing it. Now, I need a volunteer. I need a volunteer. Come on up, give her a big hand. I was going to ask you to drink this water, but I said we're going to do something different. Hold that bottle. You can remove the label if you don't mind. And I am going to give you a balloon of your choice. Once you have the label off, choose a balloon of your choice. And we're going to put that balloon inside the bottle like this, and then wrap your balloon around the lip of your bottle like that. Now we're gonna, what's your name? Becca? Becca. We're gonna have a balloon inflating contest. Ronnie and Becca. When you're ready, we want you to inflate your balloon inside that bottle. 1, 2, 3. All right, Becca, you gotta try it now. I want you to. All right, count down. 1,
2, 3.
Now, I'm not going to be cruel to Becca, because Becca can stay here and blow until she passes out. But your balloon would never inflate, Becca, because when you try to inflate your balloon, there's what inside that bottle already? Air. So there's nowhere for that air to go to make room for the air you're trying to put into your balloon. But my bottle has a hole in it. So as I inflate my balloon, it pushes the air out of the bottle to make space for the inflating balloon. Give Becca a big hand. So do me a favor, before you leave, take your balloon out and inflate it to about the size of a cantaloupe. And we're going to see what happens when we put that balloon inside some liquid nitrogen. Now, this stuff is so cold. You say, how cold? It's so cold. It's so cold. It's so cold. It's over negative 320 degrees. And if I were to leave my hand inside of it, my hand would fall off. Right? A little smaller than that one. Let's get an organic cantaloupe. Yeah, there we go. Come on, a little more. A little more. A little more. Just try to slip one in now, Becca, while you let that balloon go. Try to see if you can time it perfectly. All right, there we go. Yes, ma'am, please. We breathe in what, boys and girls? Oxygen, right? And we breathe out what? Carbon dioxide. Now, if I was holding, thank you, give her a big hand. If I was holding 2 balloons, one filled with helium, one filled with carbon dioxide, and I released them, which one would fall to the ground? The CO2. Why? It's heavy. It's more, that D word. It's more dense. So, just like your mom and dad's tires in the wintertime, when they get in the car and they crank it, and there's a little light icon that says check pressure tire or tire pressure. When cold, the air starts to contract. Right now, the molecules, we know that gas molecules are rapidly moving, but they're all confined inside this what? The balloon. So when we make the air temperature inside the balloon very cold, the air molecules are going to do what? What do you think? They're going to contract. So let's put some nitrogen inside the bottle, inside the bowl, I mean. Oh, yeah. Oh, yeah. Now, let's make some observations before we begin. Remember this sound, okay? We're going to call this rubbery. We're going to put the balloon inside the nitrogen, and we're going to wait for a few moments. If you listen very carefully, you're going to hear a change in the texture. You hear that? Now that sounds papery. Now, our balloon has contracted like an IHOP pancake. So now we've made the air inside the balloon, the molecules have contracted, right? What do you think would happen if we take the balloon out, allowing the molecules to warm back up? What do you think the balloon would do? Reinflate? That is the craziest thing I've ever heard in my life. What do you think? Somebody want to say reinflate. And what I would encourage my students, stand in what you believe. If you believe the balloon will reinflate, don't care what anybody around you says. Stand with what you believe, because there's no right or wrong in science. We just learn different ways to go by doing it, right?
How crunchy is it?
It's crunchy.
It's latex.
All right, let's see. Hold that for us, please, up high.
I think you're going to be able to.
Ladies and gentlemen, right before your eyes, you're witnessing the rewarming of air molecules. Give her a big hand. And the balloon does reinflate. That was really awesome. Talk to your neighbor about that. While you're talking to your neighbor, look to the floor. If you didn't see it, don't worry. We're going to give you a chance to observe it a little bit later. But talk to your neighbor. We're going to do some more investigating with nitrogen before we leave as well. Now, I have a friend. The children are much more compassionate than adults. I tell adults this story, and they laugh, and it makes me feel sad. But I have a friend named Bob. He's an elephant, and he lives in the zoo, right? Every Thursday, they have cheeseburgers, and Bob likes to get his with onions. So he asked if I could come to Silicon Valley, the home of innovation, to create elephant toothpaste. I need someone to help me with that. We're going to go right here in the middle, and we're going to make elephant toothpaste, I think. Our thoughts. We're going to pause on that one and come back to that one. We're going to come back to that one. And I'll tell you why. But in the meantime, we're going to make a non-Newtonian substance. At your tables, clear your tables. We're going to have about 5 stations. Put about 5 bowls and put a spatula in each bowl if you don't mind.
And then each bowl will require a can of shaving cream. So if you don't have a bowl at your table, please move around. Now, someone mentioned earlier having a pre-K special ed class. This would be a really good tactile learning engagement for them. So 1 measuring cup, there should be 5. If not, we'll share. Now, we're going to give each table a cup of glue. We have 5 bowls, correct? So we're going to get 5 cups of glue. Send 1 person to come and retrieve your materials. And then come and also get a half a cup of water. 1 cup of glue. That's more than a half. That's a little more, but yeah. 1 cup of glue, half a cup of water. One cup of glue, half a cup of water. Step number 1. Step number 1. In your large mixing bowl, in your empty large mixing bowl, combine 1 cup of glue and half cup of water and mix. In the mixing bowl. All right. No, you have to touch that handle a little bit. Okay.
There's an extra one here. So.
All right. Once you've added the cup and water together, mix. Let's save it. The contact solution. So we're going to. So you're going to put 3 tablespoons in each one. 3 tablespoons. Only thing about that thing there is very tricky. Yes, so you need 3 of those in each cup. Step 2, shake up the can of shaving cream. Shake up the can of shaving cream and measure out 4 cups. You have a large measuring cup. Measure out 4 cups of shaving cream. Tap it on the table to make sure it's compact and packed in. And then use your spatula to add your shaving cream to your glue and water mixture. Yes, you do. Five, I think, right? Once you've added your shaving cream, then go ahead and start mixing. All right, now, these are not shots. Please don't. This is contact solution. Yeah, we're just giving you 3 tablespoons of contact solution. Add it in thirds. Add the contact solution in thirds and mix it in really well. Add in the contact solution in thirds and mix it in really well. So, if we were going to add color, we would have done that in the glue and water stage. You could have added color, maybe even glitter.
And the glue and water stage.
Yep.
Okay.
Now it would be too
Hard to get it to
too hard for it to dissolve and penetrate throughout and mix evenly.
I am doing this.
So mix it in really well. Get the sides really well. We're going to bring you your third or your next ingredient. Right here, it's going to be the. So we're going to give them 3
cups.
3
I mean, 3
tablespoons.
of water.
So that's going to be borax solution. So far you've used glue, water, shaving cream, and contact solution. We're going to bring around borax solution. Make sure you're mixing the sides really well. Add your borax solution in thirds. Yeah, it's just water. So it's 1 cup of hot water and 1 tablespoon of borax powder. And you mix till it dissolves, let it cool off. So it's going to help make it less. So if you touch it now, it's going to be very sticky to the hand. In thirds, yes, ma'am. Add it in thirds. So it's coming to you now. Your slime may look fluffy now, but if you touch it, it's going to be very sticky. Adding the borax is going to help reduce that stickiness. So make sure as you're mixing, mix from the bottoms and the sides. Smack it up, flip it, rub it down. Oh no. Yeah, you sure can. Keep mixing. Keep mixing. Keep mixing. The dish soap. You got some dish soap? Like Dawn, perhaps? But at this point, we'll take whatever. All right, give it a good 30 seconds of straight mixing. Someone hold the bowl and somebody put their elbow on high and just mix it for about a good 30 seconds. Yes, we are. So, once you have a consistent mass of slime and it's not sticking, take it out of the bowl, clear your table space, and you may engage with it. Share it evenly amongst your group members. Someone can bring your items here your measuring cup, spatula, and your bowl. We'll throw away the glue cup and we'll keep the other clear cups without glue. It's all good. You just stack it there. Please and thank you.
Fun I've had.
Thank you. Thank you. Thank you. That really.
Grandsons, and I want to do all of this with them.
So I have an online class as well.
That's great.
I mail the stuff to them at home.
So it's on your website?
Yes, ma'am. I'll make sure to give you my card before we leave.
That'd be great.
Perfect.
Yeah, because I do a lot of this kind of stuff, but not this cool.
Yeah.
So.
And we have a YouTube channel too called Fun Weird Science and Spaghetti. So it's geared toward families.
You know, we do a symposium. I'm from Cast in Boston, and we do a symposium every year. I'd love to give you my card and have you come and present. That'd be great.
We'd love to.
Okay.
Let's talk.
Great.
My coworker wants to know when she put a fake fragrance in it to make it smell better, and what step?
So I would do that at the glue and the water stage.
Okay.
Yeah. What fragrance you gonna go with? Lavender?
I don't know.
Okay.
What fragrance?
Okay.
That oil.
All right. So if you hear my voice stop once, if you hear my voice stop twice, one of our team members had a great idea in terms of that sensory piece, right? Adding a fragrance to this slide. And that would be done at the glue and water stage.
Same as the glitter.
So we call this a non-Newtonian because if I hold it like this, it oozes like a booger, like a liquid, right? But if I roll it and drop it, it's gonna bounce up like a solid. A non-Newtonian can be a solid and a liquid at the same time. We'll give you a few more moments to engage with the slide. Yes.
I know some parents are concerned about borax. When you boil it in the water, does that neutralize it?
I've never had an issue. I've heard of some kids.
Found this much. Is that?
That's perfect. Yes.
Okay.
I've heard some kids have an issue with it, like irritating their skin.
Yeah, like irritating.
But I've never had an issue with it.
Okay.
And I've done it in a variety of settings with different age children.
You've never had that.
I've never had an issue.
Okay.
Yeah.
I'm wondering if it's more like if they handle the powder. I'm wondering if that causes
I would think
more
so.
of an irritant.
I would think so.
But you make it into a solution
Yep.
in advance.
1 cup of hot water. Well, that's the ratio. 1 cup of hot water to 1 tablespoon of borax powder.
Got it.
Mixed to dissolves. At the grocery store, on the same aisle in Georgia, on the same aisle with the washing powder. Yep, detergent. It's borax 100 Muatine, something like that. It's the name of the box, like a white box. But there's a restaurant in Atlanta that uses borax, Ted's Montana. It's like a grill. They're very eco-friendly.
Yeah.
They have paper straws, like dim lights.
I love it.
They but in their bathroom they have the borax powder with like a essential oil into it. So when you wash your hands, like it like exfoliates your skin. Your skin is softer, and that is better for the environment than borax. Yeah, it's very interesting. All right. Perfect. We finna find out. Hey, we finna find out. Yes, question, please.
Do you have a little Ziploc?
Yes and no. Yes and no. We got cups. And I do I had, yeah, put it in spring makeup. Yes, so yes, we do have some little to-go containers. So, moving on. You guys are great, though. Going back to my friend Fred. His name wasn't Fred. What I said his name was?
I don't know, but his breath is stinky.
Yeah, his breath from the onions. Bob. I can't forget my friend's name. I'm going to be exposed. So, going back to my friend Bob. The scientific name for water is what? H2O. We're going to be using peroxide found in the beauty salon section that's used to make like blonde streaks in the hair. And the scientific name for peroxide is H2O2. So we're going to try to see if we can release one of those oxygens and capture it. I need a volunteer. Meet me in the middle. Baby, why don't you just meet me in the middle? I'm losing my mind. All right, now, this peroxide can burn your upper dermis. The first time I did it at home, I freaked out. I don't know if I had vitiligo or anything, I didn't know what was happening, but after a few moments, your skin oxidizes and everything is back to normal. But it felt, I freaked out. I didn't know. I just saw it online. I wanted to try it, but I didn't research enough. So I wasn't sure if it was going to be reversible. I had a moment of uncertainty there. So, but if it does touch your skin, it feels like small pins. It won't make you scream and call for mama, but you definitely can feel it. So I'm going to be very careful as we pour that into the bottle. So using this science tool called a funnel, we're going to hold that for me, please. And we're going to pour in the peroxide. I'm going to ask you to take out your favorite color, put about 5 drops of food color into it. And while you're doing that, we're going to need a catalyst. Say catalyst, boys and girls. Catalyst. Now, I'm always looking for ways to incorporate conversations. So no, a catalyst is something that can get things in motion, right? To get things going in motion. So I would have a conversation with my students about Colin Kaepernick being a catalyst in terms of getting a conversation started or attempting to get a conversation started about the mistreatment of black people in our society, right? That it didn't go over as well as he intended, but he was attempting to be a catalyst for a conversation. So we're going to use dry yeast as our catalyst to start this reaction. So pour the yeast into the cup, and as you're doing it, just hold it up so we all can see it to make sure you're not doing anything shady. Now, inside your solution of Kool-Aid, also known as peroxide and food coloring, we're going to add some dish soap. It smells like Dawn. So we're going to see if we can add a nice big squirt, like my children squeeze. They don't pay for no dish soap at home. You don't need that much soap for those dishes. It's the whole bottle for 4 dishes. So now we're going to add some water in this cup here. Let's put in 2 tablespoons of water in your dry yeast and turn around so we all can see you. Okay, give me one more. They like one of those cars that CarMax in the front. They just spin around.
The only way I can turn around for all.
All right, let's see what we have there. Let's see if we can mix it up a little bit. Give me a little more. Give me one more. And use the handle of your measuring spoon to stir it up. Okay, then, yeah, that part too.
That's not the hand.
It's all good, you know. Same.
Then both sides are dirty.
So now, we're going to try to see if we can release one of those oxygens. Let's see, because we need that. It cakes up sometimes, and we don't want that. All right, let's try another one.
I messed it up.
No, you did not mess it up. You did not mess it up. I just want to make sure that we have, it's science. Things are never going to work the way that we think they should every time. All right, so 3 tablespoons of water. All right, 4 tablespoons. Okay, let's see. All right, smell that for me. Freeze, turn around, put it back where you had it. No, you smell it like you were smelling it. Now turn around so we all can see you. Because in science, we want to always discourage our students from smelling like that because it can burn your nasal passage. So we want to hold it down some and use the wafting method to lift that scent up to your nose. Awesome. Now, we're going to pour everything into that funnel quickly. Let's see if it does. Oh! Oh! And there we have elephant toothpaste. Take one finger and touch it.
You just said it's going to change my skin.
No, I did. So you were listening. That's a good job. But once that reaction takes place, then you're clear and free. How does it feel?
Warm.
I would charge you $25 to come to my spa and put your hand inside there. But it's very therapeutic. But now you made an exothermic reaction. When you add substances that produce heat, it's called the exothermic reaction. Give her a big hand. Talk to a neighbor about what you're thinking so far. I see, I think, I wonder. I see, I think, I wonder. I see, I think, I wonder. What are you thinking? What are you still wondering? Share with a neighbor. Anyone care to share out a thought or wondering?
So what is the next, like what happens to this material now that it's in a bowl like that?
So eventually it cools off. So, you know, in the very initial stages of the reaction, it's cool to touch, to feel that warmth that came out of nowhere, supposedly. But, you know, once it sits for a while, it cools off, and then it's just down the sink, yeah. But it's just, you know, you can touch it. Yeah, it's just like dish soap.
So how is
Suds.
it used to catalyst? What does it do?
That's your homework assignment. That's your homework assignment. That's a good question, and this is what we're hoping that the kids are going to do. Like, what if we use flour opposed to yeast? Like, what's in the yeast that makes it react the way that it does? That's a great question. That's a great question. Very good question. I need 3 volunteers. 3 volunteers.
Oh,
Many years ago, many of you wore one of these. And if you're fortunate enough to live long, you're going to make your way back to them again. We need 3 volunteers. Right here in the center. Oh, we're going to stand right here. We'll stand right here. Are you joining us?
Yes.
Perfect. So keep that cup out in front like this. Don't look at it, just keep it up out in front. You got to stand for this one, though. All right, right here where you were sitting. Keep the cup out in front of you. Don't tilt it. Don't look into it. Just keep the cup out in front of you. Your job in the audience is to follow the cup with water. Follow the cup with water. We're going to add water to one of these cups. Now, your job is to swap cups slowly with each other. Exchange cups. Keep the cups outright. Don't drop them. Keep going. We go a little faster than that, you know, but just not so fast to where you're trying to deceive and trick us. All right, stop there. Where is the cup of water? Right here? All right, let's take the cup and let's pour it here. Cups out, rotate cups. Follow the cup with water. Don't turn your back to us because you're trying to trick us. And stop.
Over there.
On the end right here?
Yep.
All right. This cup here. Not this cup right here.
No.
Let's count to 3, and we're going to turn it over top of her head. 1, 2, 3. Not that cup. This cup right here?
No.
Not this cup either? On 3. 1, 2, 3. All right, have a seat, you two. Drum roll, please. One, 2.
What am I looking at?
There's no water because we put in sodium tetraborate. I'm sorry, sodium polyacrylate, which is diaper powder. So the diaper powder absorbed that water before it was able to pour out. Give them all 3 a big hand. So this diaper powder is inside every diaper. So get a clean diaper from a neighbor that has a baby, and then cut it open over a newspaper and shake it out. And you can do the same thing here at home. I added too much water, and now I was like slush. So I almost exceeded the saturation point of the amount of, but it held it. So I would have the children talk about what other real world applications can we use this diaper powder? How can we use this in our world around us? Talk with your neighbor about that. Share your thoughts. How can we use this in the world around us? Once again, you can keep up with us by visiting our website, funweirdscience.com. And once again, our social media contacts at funweirdscience on Facebook, Instagram, and Twitter. And my goal is to increase student engagement and teacher efficacy through STEM. But we're not done. We're not done. We're going to see if we can demonstrate Bernoulli's principle. So here we have a handy-dandy blower with a handy-dandy paint roller. I need a volunteer. My wife doesn't like when I take the tissue at the house, so I have to go and buy separate rolls. But then when we run low in the house, she always says, you know, you got any tissue in your phone with science stuff? I'm like, no. Because if I can't use your tissue for my stuff, you can't use my tissue for your stuff. You gotta be inclusive. So, I would talk to the children here about how the wings of a bird were closely studied when the airplane was developed. According to Bernoulli's principle, it says, if we blow air over a curved surface, we're going to get high pressure and low pressure. And together, volunteer?
I'll do it.
Come on now.
This looks like fun.
She's like,
Oh yeah.
She had those deer in the
Power
headlights.
tools.
So hold it like you own it.
All right.
Say hello to my little friend. So, we're going to blow air over this curved surface. And we're going to get high pressure and low pressure together. It's going to give us lift.
So I just push this button.
Yep, and hold it up at an angle. And we're going to get... Oh, no. Ah, yeah. right, give her a big hand. Now, during your next staff meeting, I want you to do this. Right when they're talking about data and test data, and just come in there with your whole grade level and just start tissuing the whole place up. Now, our next demonstration revolves around that little clicker thing. It escapes me sometimes. And we got 15 more minutes. Egg drop. So, I need a volunteer again. We're going to attempt to demonstrate inertia, property of gravity. You want to help me with this one?
Yeah.
Yes, give her a big hand. Yes, you do. Yes, you do. This is all you're going to do right here. This right here. So,
Somebody else want to do this?
this really works with a broom that has longer bristles. But it's hard for me to travel through TSA with a long broom. So, hold that for me 1 second. What do you think would happen if we took the following? What would happen if we had a cup, and in that cup we put water to make it stable, and then on top of that cup we put a very vintage cake pan. Very vintage. I left it on the back of my truck one day and it rained. And on top of that, we added a paper towel roll. I'm going to use these paper towels. We're not promoting the waste of any materials, but I'm going to go back and reuse them in my cleanup. So, on top of that cake pan, we're going to put a paper towel roll. On top of that paper towel roll, we're going to put a raw egg. Now, we're going to pull back on our broom. Can anyone see me? This is a very short, bristle broom. So we have to get a proper placement, but the goal is to make the broom move in a straight line like that, right? So step to the side and practice that. Step to the side. Here's the thing, ladies and gentlemen. You'll catch it though. You want to catch it, yeah. That's why they have egg stains in our clothes, you know. Now, that's perfect. Ladies and gentlemen, the broom handle will hit the cake pan, but will be stopped by the edge of the table. If we pull the broom handle back from this direction and let go, what direction will the cake pan go? Point in the direction you think the cake pan will go. All right, where will the paper towel roll go? Back this way. Where will the egg go? 1 in 3 eggs should go into the cup. The force of the broom handle will not be strong enough to make the egg go in the same direction. This would be a really good science fair project if you had a wooden broom. Took an eye hook, screw into the wooden broom handle, and use a spring scale to attach to the eye hook to measure the amounts of newtons you're using to pull the broom back with, right? And then see if you have the probability of getting the consistent number of eggs to fall into the pan, to the cup. Everything in science is not working the way we think it should. Come a little closer. Come a little closer. Because we don't want to tip the cake pan forward. We want to hit it evenly. Come a little closer. That's perfect. We got a perfect stance. All right. Pull back.
I'm clearly not stopping it.
No.
Okay.
You're not stopping it. Right there is perfect.
Yeah.
3, 2, 1. Oh! She shoots. She scores. For a very brief second, there was nothing holding the egg up. And then gravity pulled it straight down. Give her a big hand. So, The force of the broom handle was not strong enough to move the egg in the same direction. It's messy, but I love it. I love it when it looks like this. This is now, thanks to the people at Delta, they have damaged my board. So that's perfect timing. So because of space, we're gonna skip the Diet Coke and Mentos. Okay. But that's a really cool geyser reaction. But we're gonna still do the liquid nitrogen explosion at the end. So here we have our centripetal force board. Centripetal force is a center-seeking force, right? Meaning if I move my board in a circular motion, yeah, stand clear because I had to tape one end because they cracked my board in baggage claim. If I keep it going like this, it's going to force everything to the center, correct? So that means if I had a cup of water, you want to try it? Don't be scared. Don't be scared. Who want to try it? Even with the damaged handle. It's only science. So, if there's one among you that may be brave enough, courageous enough to take risk. No? All right, come on up. Give her a big hand. All right, safety goggles. Put your finger through and step back this way because I literally had to tape that edge because they broke it. Are you left hand dominant? I'm right hand. Let's stick with let's not get creative today. All right, so hook that finger and using your whole arm, circular motion. Whole arm. There you go, like you. You gotta add your hips to it too. You gotta. All right, there you go. All right, stop right there. Bring it to a slow stop. I'm gonna add a cup of water to that board. Oh no, same action, hip motion and all. When you're ready, come on, keep going. Don't stop. Ah! Slow stop, slow stop. Slow stop. All right, give her a big hand. Now, we can add 4 or 5 cups of water, and it should still hold true to that centripetal force to keep everything in the center. Before we leave, if I can get you to help me tighten up your tables, and I am going to heat up some water. If you have any questions, let's talk. Any questions? Any questions? Any thoughts? Thank you. Please share that sentiment in your surveys. During my 20 years, many of those years were in school areas where there were lots of frustrations and lots of things that could make your day stressful. And my biggest benefactor was engaging kids in a hands-on approach. When I kept them busy with their hands, their mouths all of a sudden didn't talk as much, and they didn't move as much. Being disruptive. Right. So that would be to be inclusive of all your different types of learners in your classrooms. We tend to have, we teach in some schools to the bottom to kind of raise those kids up, and then in some cases to the top. But we miss sometimes the kids in the middle because they're not disruptive, they're not too slow, too low in their learning, and we tend to miss them sometimes. But I found that teaching from a hands-on perspective is a very inclusive approach. So right now, we have some water boiling, and we're gonna go over here in the middle. We're gonna fill this trash can with nitrogen. because I can't take it on the plane. So we have to fill it. And we're going to dump in some very hot water. This is about 10 liters. Of liquid nitrogen. We're going to dump in very hot water. What do you think is going to happen? Get your phones out. This is a good slow motion capture. We're just waiting for the water to boil. Talk to your neighbor about what you think is going to happen. I hope that this last demonstration shows the impact that we can have when we include all the learners in our classrooms. Give the water a few more seconds to boil. How much time do we have now? 3 minutes? Awesome. Space camp for teachers. That was one of the pivotal points for me. Honeywell used to do a program where they would send teachers to space camp. But it was a week-long integration on space exploration and STEM, and I found it to be very engaging. The Exxon Mobil, they have a week-long engagement also, math and science. And these are professional developments that I attended as a teacher that kind of changed the course. Oh yeah. If you put your foot or hand in there, yeah. Very much so. Don't do it though. All right. Then we're almost there. That's hard enough, I think. So, I'm going to dump this hot water into the very cold nitrogen. And this represents the impact that we can have in our learning environments when we take inclusive approaches to teaching and learning. Count me down. 5,
4, 3, 2, 1.
Thank you all so much for your time today.